Hello everyone, and welcome to the AI Research Roundup. I'm your host Alex, and today we're diving into some fascinating AI research. We'll be looking at a paper called VGGT, Visual Geometry Grounded Transformer. So, what this paper introduces is a neural network, VGGT, that can figure out pretty much all the key 3D information about a scene directly from images. We're talking camera positions, depth maps, 3D points, all from just one or even hundreds of pictures. It's designed to handle multiple 3D tasks simultaneously, which is a neat step forward. Okay, so figure 1 here gives a nice visual overview of what VGGT does. On the left, you see the input, a bunch of different photos of the same scene. And then the arrow points to the output in the middle, which is this reconstructed 3D point cloud of the scene. You can also see it predicts the camera positions for each input photo shown as those little camera icons. And on the right, it even generates the corresponding depth maps for some of the images. It really shows how it takes those 2D pictures and pulls out all that rich 3D information in one go. Okay, so figure 2 now gives us a peek under the hood at the model's architecture, how it actually gets from those input images to the 3D stuff we saw before. It starts by chopping up the input images into smaller patches using something called Dino. Then these patches, along with some special camera tokens, go into the main transformer part. This part uses a clever alternating attention mechanism, switching between looking at information within a single image and looking across all the images. Finally, there are separate prediction heads, one specifically for the camera parameters, and another one called DPT that handles generating the dense outputs like depth maps, point maps, and even tracking points between images. Alright, so we just saw how VGGT is built. Now, figure 3 gives us a look at its performance compared to another approach, Dust3R. It's showing the actual 3D point clouds generated from those inputs we talked about. You can see VGGT handle some tricky stuff, like reconstructing from just one picture even a painting, or from two pictures that don't overlap at all, which Dust3R seems to struggle with. And with many views, like the 32 shown for the pyramids, it still produces a good result. And notice how much faster it is in that last example. Building on those point cloud examples we just saw, figure 4 here shows us some more results, specifically the point map estimations. It really highlights the variety of scenes VGGT can handle. You've got famous landmarks like the Colosseum, some indoor shots, and other outdoor areas too. Just like before, it's taking those input images on the left and generating these detailed 3D point clouds. And again, you can see the estimated camera positions are also visualized. Okay, so we've seen the visual outputs like point maps. Now, Table 1 gives us some hard numbers on one of those key tasks, camera pose estimation. This table compares VGGT against several other methods on two different datasets, Real Estate 10K and CO3 DV2. Looking at accuracy, which is measured by AUC at 3.0, higher is better, and also the time it takes. You can see that VGGT, just in its basic feed-forward mode, gets really strong results. 85.3 and 88.2 on the two datasets, beating other methods like VGGSFM version 2. And look at the time, only 0.2 seconds, compared to 7, 10, or even more seconds for others. If you add bundle adjustment post-processing to VGGT, the accuracy gets even better, up into the 90s, while still being faster than many competing approaches. It really shows VGGT is both accurate and incredibly fast at figuring out where the cameras were. Okay, so we just saw how well VGGT does with camera poses. Now, Table 2 shifts focus to another important 3D task, dense multi-view stereo estimation, basically figuring out the depth for lots of points. This is on the DTU dataset, and it's looking at accuracy and completeness metrics, where lower numbers are better. Notice the table is split. The top methods get the correct camera positions given to them, while the bottom ones, including VGGT, have to figure that out themselves. And you can see VGGT, listed as hours, substantially outperforms Dust3R. Look at that overall score, 0.382 compared to 1.741. It's performing much better, even without knowing the ground truth cameras, getting results that are comparable to methods that actually do have that information. Alright, so after looking at depth estimation, Table 3 shifts focus again this time to point map estimation on the ETH3D dataset. We're still looking at accuracy, completeness, and overall scores, where lower is better, plus the processing time. You can see VGGT, listed as hours, significantly beats Dust 3R and Mass 3R just using its direct point map output, getting an overall score of 0.709 versus their 1.005 and 0.826. And again, check out the speed, only 0.2 seconds compared to 7 or 9 seconds. What's also neat is that if you construct the point cloud using VGGT's predicted depth and camera info instead, the result is even better. 0.677 overall. It really highlights how well VGGT can generate these point clouds and how fast it is. So as we've seen across these results, VGGT really delivers impressive performance for camera poses, depth, and point maps. The key takeaway is its ability to tackle all these visual geometry tasks together, grounded in the image features, within a single efficient transformer model, and do it incredibly fast. This unified and speedy approach is, well, really valuable for advancing 3D perception in AI. Thanks for tuning in to the AI Research Roundup. I'm your host, Alex.